afternoon, grade 12, or whatever time of the day it might be for you, morning, evening, or midnight for some of you, I'm sure. I want to carry on with our talk on kinetics. So last class we were introduced to kinetics and how we can speed a reaction up, slow it down, and so on. You should have read section 18.1. You should have done some questions from your textbook. I'm not going to bother going over those because, as you know, you have the answers in your text, which is in a PDF on your team's website. So instead, what I'd like to do is go over the last screenshot that you would have taken of Monday's notes. And you have the following 4 questions. So the first one, list 3 ways that reaction rates can generally be increased. If we want to increase the rate of a reaction, we can alter the concentration of the reactant. So if we want to increase the rate, we would increase the concentration of the reactant. If you had more moles, then you have more particles reacting. More particles means more collisions. More collisions means a greater reaction rate. Another thing you can do is change the temperature. If you increase the temperature, you're raising the heat energy. Heat energy will make the particles move faster. If they're moving faster, there's going to be more collisions and therefore a higher reaction rate. Now, the other thing you can do is add a catalyst. If you add a catalyst, you will speed the reaction up. Keep in mind, a catalyst is not used up in the reaction, so once the reaction has taken place, you can clean the catalyst up and use it again in another reaction. You can also alter the reaction rate for gaseous systems by altering the pressure. If you increase the pressure, you're decreasing the volume, which means the particles have less space to move. They're going to collide more frequently, and again, that will cause an increase in reaction rate. But please remember, that's only in gaseous systems. Question number 2, ethyl acetate reacts with a solution of sodium hydroxide and forms sodium acetate and ethyl alcohol. Suppose at 25 degrees Celsius, 2 moles of ethyl acetate reacts completely in 4 hours. What would you express the rate of reaction, or how would you rather? So remember, rate is expressed of either the amount of reactant used up over time or the amount of product being formed over time. So we have 2 moles of ethyl acetate reacting in 4 hours. So that is our reactant. So that is 2 moles on the top of our fraction divided by our time of 4 hours. So 2 moles per 4 hours, or we can reduce that and say 0.5 moles per hour. How would the following actions likely change the rate of reaction in problem number 2? You're decreasing the temperature. The particles are not going to move as quickly. Therefore, there will not be as many collisions, and you are decreasing the rate of reaction. If you increase the sodium hydroxide, if we go back to number 2, you'll see sodium hydroxide was one of the reactants. If you're increasing its concentration, there's going to be more moles of particles to react, therefore more collisions, and therefore a faster reaction rate. And lastly, ethyl acetate and water are not miscible. That means they do not mix together. So, if the reaction problem 2 only occurs at the interface of the 2 liquids, in other words, again, they're not mixing, what would be the effect on the reaction rate if we were to add a solvent to make the reaction homogeneous? So what would happen to the ethyl acetate and water if we forced them to mix together? If we added a solvent that they would both dissolve in, you're going to have the particles moving, they're going to be mixing, banging into one another more often, and therefore that will increase the reaction rate. So have your phones ready in case you want to take a screenshot. There are the answers that we just went over. The only one in number 1 I neglected to mention was if you wanted to speed up the rate of reaction, you could also adjust the particle size. So to speed things up, instead of using big chunks of chemical, you could crush the chemical up and therefore increase its surface area. Okay, so over the last couple of days I did a couple of experiments for you to help cement some of this material. The first one here, I had a couple of glow sticks kicking around at home and thought I might put them in hot water and cold. Okay, so what we have here is a hot water bath at 100 degrees Celsius roughly, and we have 2 glow sticks inserted, acclimatizing to the temperature. This one is just above freezing, again with 2 glow sticks in there, acclimatizing. So what I'm going to do is take out the glow sticks as quickly as possible, snap them to initiate the chemical reaction, and then put them back in for 10 seconds and compare the changes in temperature over those 10 seconds. So I have my timer started over here. Hey Google, start a stopwatch for 10 seconds.
Alright, 10 seconds. And that's starting now.
Already you can see the significant difference in color with the hot versus the cold. Stop. So we'll take those out very quickly. I'm going to stop right there, grade 12, not to bore you too much with my poor use of the kitchen tongs. But anyway, what I wanted you to see was the hotter the water, the faster the chemical reaction. You could see how quickly those glow sticks changed color when they were placed in the hot water as compared with the cold water. So again, the high heat energy makes the particles move faster, and we had a faster reaction rate. The next one I want to show you is a reaction I had done with Alka-Seltzer tablets. So in this case, I actually used 3 different temperatures of water. I'm also starting our next experiment. Our next experiment looks at Alka-Seltzer tablets, and now they react in hot water, warm water, and cold water. And the difference is whether or not the Alka-Seltzer tablet is crushed up. So we'll just leave those off to the side so they can acclimatize to the cold water. So I have an empty beaker. I have a balance. I'm tearing the balance to 0. Difficult for you to see on the camera, but I assure you it's tiered to 0. Placing an empty beaker on it, and then I am adding 75 mils of water, which is about 78 degrees Celsius. There's 75 mils of water. The beaker was a little bit cooler, so it brought the temperature of the water down a bit. Now, what I'm going to do next is add 2 Alka-Seltzer tablets to the balance. And now my mass of the beaker, the Alka-Seltzer tablets, and the water at time 0 is 289.00 grams. Now I'm going to place the tablets in the water, and I'm going to record their mass every 10 seconds until the mass remains unchanged for 30 seconds. So here I go. Adding tablet 1, adding tablet 2, starting my stopwatch. At 10 seconds, the mass is 287.6. At 10 more seconds, it's 287.3. To 87.19. Okay, grade 12, I will stop that there. I did continue on for approximately 2 minutes, and I did at 5 degrees Celsius water, 25 degrees Celsius water, and about 78 degrees Celsius water. Even though the thermometer in the background was showing you it was about 50 or 60 degrees, that thermometer was not immersed in the solution we were using. So, what I want you to note is that when I graph the data that I collected, the yellow is for the warm water, so you can see that as soon as I placed those tablets in the warm water, the reaction took a very, very fast start. You can see with that nosedive. The blue one took the longest time to get started. It was at the 5 degrees Celsius cold water, and then the red was somewhere in the middle. So they all eventually reacted, but it was the warmer water that had the most significant reaction rate. The reaction rate, as you can see at the bottom here, I just remind you, increases as temperature increases. A higher temperature means that there's greater energy. This leads to faster moving particles and therefore an increase in collisions. Okay, the other thing I did, the third thing, was I took Alka-Seltzer tablets and I crushed them up and I broke them into pieces so I could compare the reaction rate to the 2 large tablets, and then those large tablets broken down into 8 to 10 pieces, and then again a third trial where those Alka-Seltzer tablets were instead crushed. I just want you to see the use of a mortar and pestle.
I just want you to see grade 12. This is what we call a mortar and pestle. A lot of times pharmacists will use it. And what we're doing is we're placing the Alka-Seltzer tablets in the mortar and pestle and crushing them. And by doing that, what we're doing is increasing the surface area. So we're going from a tablet of said size to a grounded powder, which obviously you can see has more surface area.
So the pestle is the piece in my daughter's hand that's actually doing the work, and the mortar is the ceramic bowl. And again, I lifted someone else's data. It's just a lot faster for me to steal someone else's graph. But anyway, what this particular person is showing us, the greater the surface area, so the smaller the particles, the faster the reaction rate occurs. So down here, the student is showing us this is the smashed up Alka-Seltzer, and so the reaction times were very, very small, 35 seconds, 34 seconds. And then as the particle size is increased, the reaction time was a lot longer to get that reaction going and continuing. So the more particles results in more collisions and therefore a greater reaction rate. I'm going to pause there for a second just to check on my camera.
Start.
Okay, grade 12, so this is part 2 of our lesson, looking specifically at equilibrium. So there's different kind of equilibrium. We can talk about phase equilibrium, solubility equilibrium, chemical equilibrium, and this video really does a very good job showing us phase equilibrium. So you'll note here in my notes, I say it's a little bit silly, but that's okay, we're going to watch it. Just for the first 6 minutes.
Your skin tells your story. Care for it with Nivea Q10 Moisture Replenishment. Designed for extra thirsty skin, it combines argan oil with a Q10 coenzyme identical to the one made by your skin to intensely nourish and moisturize. New from Nivea.
Great, here we go.
Good, thank you.
What are you doing?
Oh, I'm just warming up some soup for lunch. Would you like some?
Yes, please.
Okay, let me put the lid back on. I don't want to lose too much water. I don't like thick soup.
What do you mean? How does putting the lid on keep the soup from getting thick? The steam still evaporates.
Well, kind of like what I learned in science today.
Really? What did you learn?
I learned all about dynamic equilibrium.
I don't know what that is. What is dynamic equilibrium? I mean, doesn't equilibrium mean that nothing happens? Objects are at rest.
Well, let me show you with this pot of soup right here. What happens when the water evaporates?
Well, it moves out of the pot and into the air around us.
Okay, I'll put the lid back on. What happens now?
Ah, that's the water. And the steam forms droplets on the pot, which moves back down into the pot along the sides.
The water changes from a liquid to a gas, but because the lid is back on, it changes from a gas back to a liquid.
So that's why you put the lid on, because the water in the gas form can't escape, so it changes back into liquid water.
That's right. But remember that because the pot is on the stove and on a high temperature, this means that the water in the soup carries on evaporating to form water in the gas phase.
Does that mean that evaporating and condensation takes place at the same time? It seems like nothing is happening.
You've got it. Overall, it seems like there's no change in the amount of liquid water or water in the gas. There's a state of balance or dynamic equilibrium inside the pot.
I understand why you say there's equilibrium, but what does dynamic mean?
Dynamic tells us that at a microscopic level, water molecules are changing from gas to liquid and liquid to gas all the time, even though it seems like there is no change.
That's really interesting. Enough talk about chemistry. That soup smells really good. Is it time to eat?
Yes, it is. Pass me the bowl and I'll dish up.
Dynamic equilibrium. To the naked eye, it doesn't appear like anything is moving or changing. But in fact, we're going from one phase to the other and back and forth.
That was a very interesting conversation about dynamic equilibrium. In today's lesson, we will explore two examples of dynamic equilibrium. The first example is called phase equilibrium. Here, substances change phase, just like the example of water in the closed container. And the second is called chemical equilibrium. In a closed container, reactant molecules and product molecules collide with each other continually. But overall, we observe no change in the number of product or reactant molecules. By the end of this lesson, you should be able to describe what is meant by dynamic equilibrium, represent a phase equilibrium and a chemical equilibrium by writing down chemical equations and draw and interpret graphs showing chemical equilibrium. To help you form a better picture of phase equilibrium, let's take a closer look at what happens to water that is placed into a container. I really can't see anything happening here from a macroscopic view. But when we look at the water from a microscopic view, it's a completely different picture. Molecules of water are leaving the liquid and moving into the air. This process is called evaporation. Molecules of water struggle to break free of the surface, and only those with enough energy can break free. We can represent evaporation by writing an equation. H2O liquid goes to H2O gas. Notice that most of the water molecules leave the surface of the water and move off into the air. However, a few very slow-moving molecules are attracted back to the surface of the liquid. We can represent condensation by writing the equation. You know that if we leave a glass of water out in the sun, the water will evaporate completely. We will see the water level dropping. But when we put a lid on the container, we prevent the water molecules escaping. Now, watch what happens. The gas region above the liquid becomes very crowded with water molecules, and so the number of molecules evaporating decreases. But at the same time, the number of water molecules returning to the liquid increases until the number of water water molecules leaving the liquid is the same as the
Take
number
note
of
of the
molecules
arrow.
moving from
That
the
is
gas
new this
back to
unit.
the liquid.
We no longer
The
have a
rate of
single-headed arrow.
evaporation is equal to the rate of condensation. Notice that overall, the number of molecules in the air above the liquid is not changing. We call this a phase equilibrium and represent it by combining the two equations. If we heat or cool the flask, we will affect the rates of the reactions. So it is important to note that phase equilibrium is established under specific conditions. Now, phase equilibrium is the...
I'm going to stop her there and caution you again to her last statement. It's very important that equilibrium is established at a certain temperature. So if you change the temperature, you are also changing the equilibrium. Okay, so here we are again, and you'll see in red, this video might seem a bit silly, but it is effective. So hopefully you caught the idea. Equilibrium, dynamic equilibrium, internal movement. You can't necessarily see the particles, but they are moving. All right, she also referenced a closed system and an open system. A closed system is one in which nothing gets into the system, nothing leaves the system. And it's important to note whether or not we're talking about solids, liquids, aqueous, or gaseous systems. So if I just move to the next slide, I think I will better explain for you the difference between closed and open. On the left, we see a closed bottle of pop. That is definitely a closed system because inside that pop, not only do we have the sugary solution, but we also have gas particles within that solution. So once we open it, like I have over here on the right, once we open that bottle, gas is escaping, so it's now considered an open system. Now, this beaker of water, or whatever solution it is, in the middle, does not have any gas in it. We're not worried about any gas. We're not worried about any gas that might be sitting on the top. All we're worried about is the solution. So even though there's no lid on it, we can still consider it a closed system because there is nothing entering or leaving the system that we are worried about. So, interesting to make that connection, that distinction. Now, I want you to take out your pen and paper, which I hope you have out already, and your periodic tables. For those of you who left your periodic tables at school, I have posted a copy of one for you on Teams. If you go into Files, you'll see periodic table. And what I want you to do now is write out for me a balanced chemical reaction, including states, for calcium chloride and sodium sulfate reacting. Pause this video, write it out, and once you have your balanced chemical equation including states, then unpause. I'm watching. I can see if you're trying. I can see if you're pausing. Okay, so you should have written CaCl2 for your calcium chloride. Calcium with a +2, chloride with a -1. Flip-flopping gives us CaCl2. When you look on the back of your periodic table at your table of solubilities, take your right index finger, remember it has to be your right index finger, scroll down under chloride and see if you see calcium there. And you will find that calcium dissolves in water, calcium chloride. For sodium sulfate, sodium is a +1, sulfate is a polyatomic, so you found that on the back of your periodic table. It has a -2 charge, and so when you flip-flop, you have Na2SO4. You also remember, I know you do, because you're smart little critters, that anything from group 1 is soluble. So because sodium's from group 1, you automatically wrote AQ after it. Now, when those two react, you have a compound and a compound reacting. Remember, that's a double displacement reaction. They switch partners. So you have the sodium joining the chloride, the calcium joining the sulfate. So you have CaSO4 and sodium chloride, NaCl. And again, you're checking your table of solubilities, and to your surprise, calcium sulfate forms a precipitate. So you should have written a little S beside it. and beside the sodium chloride, an AQ. Now, according to the collision reaction theory, what happens is you have calcium ions and chloride ions swimming around in a beaker of water, sodium ions and sulfate ions swimming around in a beaker of water, and what happens when those ions collide, if they collide enough and in such a manner with enough energy that they reorientate themselves, they will form something new. So what I've done here on this slide, and I want you to ooh and ah please, because it took me hours to make this slide. So this is a very special slide, very important slide. Had we been in KV High School, you would have gone into the lab and you would have actually made up a calcium chloride solution, you would have made up a sodium sulfate solution, and you would have carried this reaction out. However, we have to make do, so what I did instead was make this beautiful, have I mentioned how beautiful this slide is? And in this first beaker, it's supposed to show you the calcium ions swimming around, the chloride ions swimming around, and you'll notice there's 1 calcium for every 2 chloride, 1 calcium for every 2 chloride. And then of course you know these are water molecules. Now I will get rid of these, we don't need these anymore. This is what I was using to do my beautiful diagram. So I will get rid of my sample molecules. Beautiful. So again, you see those ions swimming around. If you had supervision, you could see those. Obviously if you have that solution, you wouldn't see the ions with the naked eye, but that's what's in there. Similarly with sodium sulfate, we have sodium ions moving around, sulfate ions moving around, and again, I tried to show you the ratio, 1 sodium for every 2 sulfate. However, I think I messed that up somehow. I'll have to fix those into 2 sulfates down here. Nope, yes. Nope, we're good. Okay, 2 sodiums for every sulfate, 2 sodiums for every sulfate. So, we mix those 2 beakers of water together, and we get this beaker. So what this is supposed to show you is, it's a cloudy solution because that calcium sulfate precipitates. And at the bottom here, this little mess is my best rendition of what calcium sulfate formula units look like as they're clumped together in a solid. And again, there's some particulate throughout, which is why it's cloudy. And then water. And then of course we have our sodium chloride in solution. So, we should have in 1 beaker, these 2 mixed together. We should have the sodium chloride ions mixed together with the calcium sulfate on the bottom. I separated them because had you been in the lab, you would have used filter paper and you would have separated out this white calcium sulfate. That would have been separated and placed on your filter paper. And then what you would have had left is called the filtrate. And that filtrate should only have sodium and chloride ions in it. That's what you knew way back when you were itty bitty in grade 11. But now that you're all grown up in grade 12, we're introducing something called equilibrium. So again, if you had been in the lab, what I would have asked you to do is take this filtrate and analyze it. I would have asked you to perform some tests to see if indeed you just had sodium ions, chloride ions, and water molecules. In the lab, you would have had an aha moment, and you would have noticed that you don't just see Na+, you don't just see Cl-, but you actually would have also found some calcium ions and some sulfate ions. And you would have come running up to me and you would have said, Mrs. Tate, that doesn't make sense. The calcium sulfate should have been left behind in that filter paper. But what actually happens, at the same time you're mixing these 2 reactants together and they're forming these 2 products are mixing together and forming these 2 reactants. So what we have is a sense or a state of equilibrium where the reactants form the products form the reactants, and it goes back and forth in what's called a dynamic equilibrium. And as the video said, that dynamic equilibrium gives a particular equilibrium value that's only good at a certain temperature. So if you heated that up, your equilibrium would shift. So let's talk about shifting that equilibrium. I know that none of you would ever quarrel with your siblings, especially when you're stuck at home on lockdown. But let's just imagine that somebody, not you, maybe gave a little, I don't know, a shoulder punch to one of their siblings. I'm guessing that that sibling would have given an equivalent shoulder punch back. That's similar to what happens with dynamic equilibrium. If you make a shift to the system, it's going to want to shift back to make it so that shift never happened. It's going to want to fight to get back to where it was. So what can we do to shift an equilibrium? What can we do to shift and make more product? We can do either of these three things. We can alter the concentration, the temperature, or as I said previously, we can change pressure, but only if it's in a gaseous system. If you decide that someday you want to be a chemical engineer, I would be extremely proud, but if you did decide one of your jobs as a chemical engineer might be to look at a chemical reaction and to somehow figure out a way to increase the product without causing any environmental damage, with keeping the finances under control, and so on and so forth. So you would have to have an understanding of Le Chatelier's principle. You would have to know how to increase the product by shifting either the concentration, temperature, or pressure, or maybe all three, to keep, as I said, the environment safe and also not to cost millions of dollars. So rather than explain this slide, I think it best if I just work through some examples for you. In years past, I would ask students to memorize that, but there's really no need. It makes common sense if you look at some examples. I'll come back to this slide in a second. If we look at these examples, the first one, water is being heated up. It goes from its liquid state to its gaseous state. What if the container is heated? If you're heating a container, what are you doing? You're adding heat energy to it. Where is the energy in this chemical reaction? It's on the left side, which you already know from Unit 1 means it's endothermic. So if I'm adding more energy, there's already energy on the left side, it's like I'm adding more reactant. So adding more reactant is going to make the system want to get rid of it, to go back to its normal state. So if you add more reactant, the system is going to want to shift right to use it up. So it says you are in a sense adding more reactant, therefore more water vapor is going to be made. It's going to be shifting to the right. Let's look at the second example. We have water and it's breaking down into its ions, the hydronium ion and the hydroxide ion. Now we're adding a few crystals of sodium hydroxide to the container. So you look at that equation and you say to yourself, self, there's no sodium hydroxide there. I don't know what that Tate lady is talking about. Why is that going to have any relevance to this question? Well, remember, anything from group 1 dissolves in water. So if you take a crystal or a pellet of sodium hydroxide, see the S there, it means it's solid, and you put that in water, it's going to dissolve. And that means it's going to split up into its ions. So you're going to have Na plus and OH minus. So in essence, what you're doing is adding more hydroxide ions. Where are the hydroxide ions in the equation? On the right side. If you add more, what are they going to want to do? They're going to want to be used up, and so it's going to move to the left. So in this case, the equilibrium is going to shift left. Okay, you're doing awesome. 2 more. Here we go. Calcium carbonate, we're going to heat it up. So that's a piece of chalk. We're going to heat it up. And when we heat that chalk up, we're going to get the following products. In this case, once we heat it up, we have it in a beaker, we're going to remove the CO2 from the container. So we're going to remove this gas. The gas is on the product side. So if I take this product away, the equilibrium is going to want to shift to the right to make more equilibrium, to make that equilibrium stable again. Once you remove the product, it's going to want to shift right to try and compensate. So the equilibrium is going to shift right. And lastly, we have vinegar solution, aqueous, breaking down into its ions. We're going to add a few drops of pure CH3COOH. So we're adding pure CH3COOH. Even though it's liquid, it's going to be like we were adding reactant. We're adding more reactant, the system's going to want to use it up, and so it's going to shift right to try and form more products. Okay? So the suggestions I have for you, if you're adding reactant, it's going to shift to the right. Adding product, it's going to shift to the left. You take away reactant, it's going to want to make more, so it will shift to the left. So these ones are pretty straightforward. Temperature, the advice I have is just treat that temperature, that energy, as if it were a chemical. So if you're removing energy, treat it like you were removing a chemical. The pressure is a little bit more confusing. The pressure only pertains to gaseous systems, so keep that in mind. Pressure, gaseous systems. Now, for pressure, we're looking at the side that has either fewer or more molecules. So, if you're increasing the pressure, it's going to want to relieve that pressure, and so it's going to go to the side with fewer gas molecules. So you look at the coefficients in front of each of the gases. If you decrease the pressure, it's going to favor the side with more gas molecules, and we'll see some examples of that later. Okay, the last thing I wanted to go over in this lesson is what's called equilibrium constants. So there's two ways to express how far a reaction has gone to completion. One of the ways is equilibrium constants. We'll talk about the other way on Friday. Equilibrium expression, equilibrium constant, if the value is greater than 1, it means the reaction is going to go, it's going to want to favor the products it wants to go. If the equilibrium expression is less than 1, it means the reactants are favored and it doesn't want to go. One thing you're going to love is that Keq has no units. Super fantastic. So you're never going to lose marks for not having units because there are none for Keq. Now the expression is kind of fun. The expression needs square brackets. See these big square brackets? Those big square brackets mean concentration. So whenever you use those big square brackets, you're inferring, you're telling the reader that you mean moles per liter, or molarity, concentration. So this example is clear as mud. What they're doing is they're writing the products on the top, the reactants on the bottom, and then they're raising the concentration to whatever coefficient is up front. I will do example for you to help clear this up. But a couple of things. First of all, we only ever include aqueous systems, aqueous compounds, elements, or, I guess you wouldn't have an aqueous element, but anyway, aqueous solutions or gaseous. We don't include solids or liquids because they are pure, solids are pure, liquids are pure, and so therefore they wouldn't have a concentration because they're pure. It's not blah 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 per liter, it's pure. So these Keq expressions only include aqueous and gases. What did I say? Keq expressions only include who? I didn't hear you. Aqueous and gaseous. Does Keq have units? Pardon? Hello? Keq does not have units. Alright, one example, then I'll set you free with your homework. Colorless gas, dinitrogen tetroxide, and the dark brown gas, nitrogen dioxide, exist in equilibrium with one another. So there we are. The reactant, the product, and the double-headed arrow, which means the system is going back and forth, back and forth. A liter of gas mixture at equilibrium contains 0.0045 moles of N2O4, dinitrogen tetroxide, and 0.03 moles of NO2. Write the expression for the equilibrium, and I have to fix that spelling, constant, and calculate the equilibrium constant. Okay, first of all, let me fix that spelling, that's bothering me. Beautiful, okay. First of all, take note, it says a liter. Friday's lesson, maybe Monday's lesson I guess it will be. Monday's lesson we're going to talk about ice tables, and that's going to be very important that you notice the volume. So take note, this particular volume is 1 liter. So if you have 0.0045 moles and the volume of the container is 1 liter, you know the molarity is 0.0045 moles. So remember the KEQ expression, we're going to put the products raised to their coefficient over the reactants raised to their coefficient. Remember the coefficient is the number up front. So I have NO2, concentration, raised to the 2, N2O4, raised to the 1. This is a gas, yay, I can include it. This is a gas, yay, I can include it. Then I simply fill in the numbers for the concentration values of NO2 squared. Concentration value for N2O4, and then I use my handy dandy calculator, 0.03 squared divided by 0.0045, and I should end up with a final KEQ value of, drum roll please, nothing. Look at that, I deleted it. Alright, that's alright, I'll take my handy dandy calculator and figure it out for you. So, again, 0.03 squared, and then divided by 0.0045, and I get a KEQ of 0.2. And again, no units. Excellent. So you can see at the tiny bottom there what your homework. Okay, so your homework 7 through 10 on page 557, and please remember grade 12, you have to read the textbook as well. Don't trust that I'm going to remember everything in these short little video clips. So read all of your textbook 18.2, then do those questions at the end, check them because as you know you have the answer key posted on Teams. And now get out your phones because I want you to take 2 screenshots. So here's the first one. Okay, I'm smiling. Okay, cheese. Okay. Alright, next one. Cheese. I'm smiling. Okay, perfect. Alright, so you're reading 18.2, you're answering the questions at the end of the section, and then you're coming here and you're doing these 2 screenshots, questions 1 through 8, and then when I see you on Friday, I will start the lesson by going over these 8 questions. Okay, take care, be safe, bye.